Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to everybody. So this is we will have a new topic this week. So the topic will be a discrete Fourier transform. Okay, so this is actually the real implementation of a Fourier transform, a practical implementation, because previously we have learned several weeks on DTFT, discrete time Fourier transform. So actually, the DTFT, discrete time Fourier transform, is just a theoretical, right? So conceptual, but implementing practically that DTFT, so we should do DFT, so which is what we call a discrete Fourier transform. So we will see what is actually a DFT. We will develop the concept first, and then we will look on several example after that. And starting from this week, because this topic is not covered in test 1 and test 2, the DFT, filter design later. So we have another 2 weeks for filter design. So this is where most of the final exam question will be focusing on these topics, which is DFT and filter design. Okay, so need to focus more because as I mentioned in WhatsApp, so 2 of the question, 2 out of 4 is heavily actually related to this topic, so which is a DFT. Okay, so before we go to this DFT, so let's do some recap so that we have a good understanding on the basic of what is actually Fourier transform. Okay, so this is a Fourier transform. So why we do Fourier transform? Because we want to do analysis in a frequency domain. Okay, and we have seen several reasons why we do this, why we do a frequency analysis, a spectrum analysis. So if you read on this slide, so we have an input. Okay, so we have input. We do analysis on input. So we do also analysis on output. This one, spectral analysis on output. So that one is input, output. And we do spectral analysis also on the filter. So this is the filter. So we have input. Over here, there is outputs, and then the filter. And we have a very specific reason why we do Fourier transform on each of the component. So for the filter, so what we do is actually, let's start with the input. So for the input, actually what we are trying to do is when we do analysis on input, so we are trying to identify a noise or unwanted signal. Okay, so because unwanted signal normally is, we want to remove that. So we want to remove. Unwanted signal doesn't mean it is a noise. So it can be not noise. Okay, so we have plenty of application on that. So that's why we sometimes we just call it unwanted signal. So the one that we want to remove. So that one is the analysis, the spectral analysis on input. So for the filter, so why we do analysis on the filter? Because we want to check what will the filter do. Because the filter will do the removing, or maybe boosting the value, okay, boosting the frequency, or maybe retain it, or just reduce it. So this is where we are checking on the magnitude. On the magnitude, we will check that. So if the magnitude value of the filter is 1, so means that that frequency will be retained 100%. So if the magnitude is 0, it will be, that frequency will be removed 100%. If the magnitude is greater than 1, means that that frequency will be boost. Okay, so you will increase the amplitude of that frequency. So that's on magnitude. We have seen on phase also last week. So what is the characteristic of this phase? Phase is we do analysis on phase because we want to know whether there will be a delay at the outputs. So that the one is very, very important because for example, again the example. So if we have I think just today I give you one example, the application on a crossover for speaker. So because this speaker has actually has a 3 speaker. Normally the speaker will have a 3 speaker, 3 sub speaker, or at least it has a 2 sub speaker. And this is where actually we are actually separating the signal. So one for base, one for Twitter, at least two. So delay is actually very important because we doesn't want a delay on the base and delay on the Twitter becomes a different delay. So it will be a chaos. Okay, so we need to make sure that the delay is the same, or at least the delay is the difference of the delay will be very, very, very small. Okay, so at least that one. But ideally, it should be the same delay, because on that application, we are separating the signal. So one signal goes to one sub-speaker, another signal is going to another sub-speaker. Okay, so those are the two things why we are actually analyzing the filter in on the spectrum. Okay, and then at the output, so we are just checking check which frequency have been attenuated, because most filter is not an ideal filter, and because it is not an ideal filter, so we need to check the effectiveness of the filter. So how to check that? So we can check it on the at the outputs, whether it is a good output or not a good output, right? So those are the reasons on the three component: the input, output, and the filter itself. And to do that, if you want to go to the frequency domain, so we need to do a Fourier transform. And we have seen this, if it is a xt is actually a continuous time signal. So we will do the original Fourier transform. So this is on the continuous time signal. And what we'll get is a x capital F. And that capital F is actually what we call a physical frequency. And it can also be represented by angular frequency, that capital omega. So then we will have that omega, which is in radian. Physical frequency is in hertz. But in this course, so actually we are focusing on a discrete time signal. So how to get from this continuous time signal to discrete time signal? So actually we do sampling. So we do sampling with Fs. And what is Fs? Fs is actually number of samples in 1 second. All right, and this is actually the relationship T equals to N over Fs. And if we do Fourier transform to this discrete time signal, so actually what we do is a discrete time Fourier transform. This is what we call a DFT. Instead of Fourier transform, so we are actually doing a discrete time Fourier transform. And what we will get is not x capital F. What we will get is a x a small f. And that a small f is actually what we call a frequency ratio or normalized frequency. And what is the relationship? This small f is actually equals to f over our fs, so which is the frequency sampling. And again, so we have angular frequency for this small f, so we use a small omega, so it is a 2 pi f, right? And this is that's why this is just a radian. This is a radian per second, because hertz is actually 1 over s, so that's why we have this second, radian per second. And small f doesn't have any units, so and then this small omega just radian, and the range is a 0 up to 2 pi. So we have seen this. So this is on the x-axis. So, but what is the problem here yet is n this time is already discrete, but this small f is actually still continuous. To practically implement everything must be in discrete. Okay, but this f, this small f, is actually still continuous. If we are looking at this relationship, capital F is continuous. This is just divided by some constant, so it doesn't change that this small f into a discrete values. Okay, so this is where we need to do a frequency sampling, so that we will have a discrete frequency. This f, we're going to convert it into k, so which is a discrete frequency. So then we will have a complete everything in discrete. So n is actually discrete. This k is discrete. So we should have 2 times of sampling, 2 sampling process. And to do that, and what is actually n? So this is with fs, and this is with n. If fs is the number of samples in 1 second, and n is actually a number of samples in 2 pi range. So why 2 pi range? Because this omega, the range is 0 up to 2 pi. Okay, so you're going to divide this x-axis of 0 up to 2 pi by n, by capital N. Okay, so that's the number of samples. And doing that, so how to do that? So this is, if we do that, so actually what we do is a discrete Fourier transform. So this is what we call a discrete Fourier transform. So we drop the time because now the one which is discrete, not only time. Both are now discrete. Everything are discrete. Time is discrete. The frequency is also discrete. So that's why we call it discrete Fourier transform, a complete discrete Fourier transform. So you have a discrete time signal, xn, and then you do a DFT, then you will get your capital X of k. So this is a frequency response in discrete frequency. This is a discrete, a frequency response of a discrete time signal. This is a frequency response of a continuous time signal. Okay, so then we have this relationship, which is you doesn't have to memorize. Everything is in the formula list. Okay, in exam you'll be given the formula list. So this is what we can see that this is a small f. Small f. What is the relationship with k? So it is a k over n. With omega, it is a 2 pi k over n. See, so we need that n because this is the f, this is omega going to k. So you will see that capital N. But for f, this is a capital F, which is the physical frequency. So the original frequency. So from this k into that capital F, so this is actually the formula. So you will see both this n and this fs, because it's going through a two sampling process. So one for time, another one is for a frequency. So what is the relationship? Fs k over n. Okay, so what is k? Again, k is the discrete frequency. Okay, so these are actually all the 5 frequency that we have. Originally, it is a physical frequency, capital F, until the real practical implementation. So actually, we have k. So this is a discrete frequency. And we have another 3, which is a small f, small omega, and capital omega. And so we have seen also 3 types of plot. Okay, so this is very important. So we need to, because every time you do a plotting, so either in test, exam, or your assignment, so you should know which one actually you are plotting, because analyzing the spectrum, so you should know what is actually the anatomy of the plotting. So this is the whole plot. We can see that this is the range if you are using this k, right? K. So this is k. So you are actually plotting from 0 up to actually n minus 1 up to here, one sample before n. Okay, if you are using omega, so actually it is from 0 and then pi and then 2 pi. So that's the range. So this is a whole plot. Shifted plot. So you're going to shift this part. So shift this part into a negative frequency. So that's why it will start from a negative frequency from minus n over 2 for k up to n over 2 here. We have another one, which is a half plot. So this is actually most software will do this half plot, because half plot is enough to do analysis, because your maximum frequency will be at pi, this one. If you are using k, the maximum frequency will be n over 2. If you're using a small f, so your maximum frequency will be 0.5. Okay, so for analysis, you doesn't need the other half of the plotting. And this is just for plotting, because plotting is mostly it will be a visualization for us to do the analysis, because it is a graphic representation of the spectrum. But for calculation and everything, you should have the complete formula. Okay, so actually the whole plot. So we need that everything for calculation. But for visualization, which is the plotting, so actually half plot is enough. Half plot is enough. Okay, because those are the maximum frequency. And if you are referring to this physical frequency, so actually your maximum frequency will be fs over 2. Okay, because from the Nyquist frequency, so what is your fs? Fs is supposed to be equal to fn 2fn. Okay, 2fn. So that's and fn is the maximum frequency, right? So that's why here is actually just a fs over 2. So that will be your maximum frequency. Okay, all right. So any questions before we start on this DFT? Because this is the basic on the Fourier transform. This is what we have. So everybody needs to understand this plotting first. All those notation, all those 5 frequency type. Okay. Okay, let's move to this discrete Fourier transform. So how do we do it? Because in this topic is mostly on how we do the frequency sampling. And it is actually not that complicated. So in digital system, I just going to read this thing. In digital system, all value must be in discrete. However, discrete signal in time domain that undergoes a DTFT will produce a continuous frequency value in frequency domain. Thus, it is impossible to compute Fourier transform in a digital system. Okay, I already explained this thing. And to overcome the problem, discrete Fourier transform is introduced, where both time and frequency are in discrete form. So this is where we will get this K. K is the discrete frequency. And how to do that? So what we will do is a frequency domain sampling. In time domain, sampling is based on TS. TS is sampling time. Okay, so where T, this is a relationship, T equals to N TS. So this means that every period of TS, one sample is taken. Right? So that one is actually in the time domain. So if you have any signal, so whatever the signal is, this is T. So you're going to have, if you want to do some sampling, so let's say this is TS. So let's say TS is equals to 0.1 second. So means that, so every 0.1 second, you will take one sample. So this is one sample, and then maybe over here. So this is another sample, and then taking another sample, and so on. Right? And what will be the frequency of this? So the F will be 1 over 0.1, which is 10 Hertz. So that's sampling in time domain. Okay, so we are referring to TS, which is the sampling time. So, and based on that, because F is actually 10 Hertz, so in 1 second, we will have 10 samples. Okay, so that's actually what a frequency represents. So 10 means 10 samples in 1 second. Okay, so if you have a Fs equals to 1000 Hertz, means that you're going to have a 1000 samples in 1 second. Okay, so but now we will do a frequency domain sampling. In frequency domain, similar process is used to sample the frequency domain as shown in figure below. One sample is taken at each, now we call it delta omega. Time, it is TS. In frequency, so we call it delta omega. So what are the range that we have? The range is 0 up to 2 pi. Okay, so this is a whole plot. So now we are referring to whole plot. So the range is, if we are using this small omega, is from 0 up to 2 omega. So doing sampling is quite easy. You just divide that. So this is actually, if you count, so this is a 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually this is 10 samples. So the first sample is at 0. And then this is the second sample at delta omega over here. And this is at 2 delta omega. So this is a 3 delta omega. And then 4 delta omega up to here, this is 9 delta omega. Okay. So this is up to here. So this is actually a 9 delta omega. And then 2 pi. At 2 pi, we actually don't take a sample. We don't take a sample at 2 pi. Because 2 pi, this is actually equals to 0 pi. Right? Because this is angular. 2 pi is actually equals to 0 pi. We already have a sample at 0 pi. So we don't take sample at 2 pi. So what we have is from 0, if in this case the n is equals to 10. So then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll take sample from n equals, this is k equals to 0 up to k equals to 9 only. So no sample on 2 pi. Actually, not no sample at 2 pi, we already have a sample on 2 pi. So which is at 0. And to summarize that, so actually this is the formula. This is what is the delta omega. Delta omega is just that 2 pi because the range is 2 pi. And then just divide by number of samples that you want. Okay, so which is the capital N. So where N is the number of samples taken from the frequency domain. If in time domain, T is equals to NTS is used to sample the time in frequency domain. So we use that omega equals to K delta omega. So this is the relationship. Time domain, T equals to NTS. Frequency domain, that omega is actually equals to K delta omega. N is the discrete time. This K is the discrete frequency. To sample the frequency where N and K is an integer number. It must be integer. N must be integer, K must be integer because it is a sample. And more facts, in time domain, Fs must be chosen as Fs greater than 2Fn to avoid aliasing. Okay, so we have seen this. This is based on Nyquist theory. So how to choose Fs? Because when we do sampling, we should have enough samples to represent the signal. And how to do that? So we need to follow this formula. Okay, so we need to choose Fs at least greater than or equals to 2Fn, where Fn is the maximum frequency. Okay, for example, for human hearing, so if we have an audio signal, so you need to actually, because the maximum frequency that human can hear is actually on maybe I think 22 kilohertz. Okay, 22 kilohertz is the maximum frequency that human can hear. So if you have an audio signal, so you should sample that signal. The Fs that you need to choose is at least 44 kilohertz, double the maximum of the frequency. So you should do that. So at least 44 kilohertz, the Fs for audio, because a human hearing is up to 22 kilohertz. In frequency domain, aliasing can be avoided when N. So this is the rules. This is the rule for frequency. When N is chosen as N greater than or equals to length of the signal in the time domain. Okay, this is actually more straightforward compared to this one because what is Fn? Fn is actually different from one signal to another signal. Okay, from one application to another application, it will be different. So as I just mentioned, give you one example, audio. So the maximum frequency is 22 kilohertz. For ECG, so maybe the maximum frequency is just, I think maybe just 200 hertz. Okay, for ECG, maybe 200 hertz. So very low compared to audio, human hearing. So that will be different from one application to another application. But in frequency domain, this omega, it is a more straightforward. So we just choose N. This is a capital N. It must be greater than or equal to the length of the signal in the time domain. So whatever the signal that you already have, the discrete time signal. So you just need to know what how many samples that you have in that signal, right? And then pick this capital N, at least the same amount of samples that you have in time domain. More is better, of course. Okay, in doing sampling, if you have more samples, it will be better. So, but this is the rules to avoid aliasing. Okay, so those are the two rules. One is in time domain, you need to follow Nyquist, and in frequency domain for frequency, so at least it must be equal to the number of samples in time domain. So then in computing a DFT, the frequency range will always start at omega equals to 0 and end at omega equals to 2 pi minus delta omega. So this is what means this one. So what is actually this one? So this is actually 2 pi minus delta omega. Okay, so 2 pi minus delta omega, so you will get, if n is 10, so you will get a 9 delta omega. Okay, and then this is the formula. So actually this is from DTFT, but what we have now is, what is the omega? If we refer to this slide, omega is actually equals to 2 pi k over n. Okay, so actually omega is actually 2 pi k over n. So, and previously, what is x omega? So we have actually this is n from minus infinity up to infinity of xn e minus j omega n. So this is DTFT. DTFT. So what we do is just we just replace that omega, this omega, with this one. So what is that omega? Omega is a 2 pi k over n. So this is what you get now. Okay, so then even the bracket is different now. So we are not using a normal bracket. So this is a square bracket. Because in this course, we are trying to be consistent. If the index is discrete, so we will use a square bracket. If the index is continuous, we're going to use a normal bracket. Okay, so this is a normal bracket because omega is continuous. K is discrete. What does it mean by discrete? The value must be integer. So it must be 0, 1, 2, 3, 4, 5, those kind of things. It can be negative 1, negative 2, negative 3, doesn't matter. But it needs to be. It can be positive or negative, it must be integer. So this is what we have, and then this is the inverse formula. Okay. Previously, in DTFT, the previous formula is actually using integration. So, but now, because everything is discrete, so we can use summation. So now we can replace the integration with summation. So then it is easier to compute, easier to implement. Right? Because the integration is a continuous formula. So you don't do integration in a discrete system. Okay, we do summation. So integration is just a theoretical and conceptual calculation. You can do it by your hand using by hand calculation, but not on computer. Actually, not on computer. Okay, so actually what we do is we convert that into summation because everything is now discrete, so we can do this. Okay, so we can do the forward and inverse. So using summation. Okay, all right. So those are the things. Those are the basic of what is actually DFT. So what we do is just this one actually. So we do sampling in frequency domain. Then doing that, it means replacing that omega with 2 pi k over n. Okay, so that's actually that is DFT. So everything else is the same concept. Essentially, we are doing the same concept. And if you realize, actually, most of you in test 2. So for the question 2, when you are asked to plot the magnitude, okay. So what you do is not a DTFT. The one that you plot is actually a DFT, because you are choosing just several values and then you plot. Okay, actually, most of you doing that. So actually, you're not doing DTFT. So what you do is you already done DFT in test 2, choosing several points and then plot. Okay, so but of course the actual answer is the accurate answer is you should do DTFT, which is you need to sketch the cost signal, because actually sketching cost signal is not that complicated. So you can have a cost signal on from 0 up to 2 pi range, no problem. So you can sketch that actually. Okay, but actually most of you just do DFT. So it means that before going to this chapter, you already done DFT. So actually that's actually one of the why we do DFT, because actually we cannot compute everything. So we need to select points to compute, even computer. So we cannot do a continuous calculation. So we need to pick points. Okay, let's see. So now this is example 1. So hopefully we can finish this example within this first part, and then we will do another example in second part. Okay, on Thursday, so we will do another example. All right. So in this example, we have a HN. So what is a HN? So can you name what is a HN? Anyone? So what does it call? It has a name. What is a HN? What is the name for HN? Impulse response, yes. Okay. So HN is impulse response. If this is XN, then it is a signal. So just a signal, there is no name. So HN is a system, representing system. We call it impulse response. And now, in this impulse response, so we have 1, 2, 3, 4. 4 samples only. Okay. So, and if referring to filter, so this is the filter. So this is our filter. And obviously, this is FIR. And if we look at the coefficient, so if we go for coefficient, so coefficient A is equals to 1, and then our coefficient B is actually equals to H, equals to those things, right? So in terms of a filter coefficient, so we have seen this because for FIR, A is fixed to 1. So this is always 1 for FIR. So IIR, yes, you can have A other than 1. Okay, so because the length of the signal is 4, so 1, 2, 3, 4, so that's the length. So this is actually the first thing. The first thing that we have learned in first week is on the length of a signal. So HN is a system, it's not a signal, but it is a vector. So this is the length of the vector. So even though it is, we call this a signal here, so this is actually representing a vector. Okay, so not to confuse with what we call a discrete time signal that we have a XN. XN is a signal. This is a system. So sometimes we just call it a signal because it looks similar to signal. Because everything is just a vector. Everything is just vector. So you can also call it just a vector. So if it doesn't want to be confused, so this is just generally a vector. And the length of the vector is 4, so we choose n equals to 4. So this is the minimum. Because what is the rules? So to choose n, this capital N, at least it must be equals to the length of the time domain signal or vector. Okay, so now we choose n equals to 4. So we choose 4 if other value of n is not stated. Thus, DFT is computed for 0, k from 0 up to 3, right? Because n is equals to 4. So we have, what does it mean by this? What is n? N is the number of samples in frequency domain. So it means that if n equals to 4, you're going to have, you're going to look at a 4 different frequency. Okay, so you have a 4 different frequency. So let's say this is a k. So you should have 0, 1, 2, 3. So this is, that one is a H. So you should find what is a H0, H1, H2, and H3. So now you have 1, 2, 3, 4, means that 4 samples. But of course, if you convert that into omega, so what is actually omega? Omega is 2 pi k over n. And because your n is 4, so this is actually pi k over 2. Okay, in our case here. So when k is 0, omega is 0, k 0, omega is 0. When k is 1, this is actually pi over 2. This one will be pi, and then this will be 3 pi over 2. Okay, in terms of omega. So actually we are just referring, if we choose n equals to 4, so we're going to compute this spectrum on omega equals to 0, pi over 2, pi, and 3 pi over 2. So we're just looking at this 4 frequency only, right? So that's what it means. So we are sampling the frequency. But in terms of k, so this is a 0, 1, 2, and 3, because k is supposed to be integer value. Right? And then what is the delta omega? Delta omega is 2 pi over n. So which is pi over 2. So you can see it here, because this is the first frequency that we are going to look at, because this is where the delta omega should be. So we're going to take sample every pi over 2. So that's why the first one is pi over 2, and then pi, and then 3 pi over 2. Okay, so that's what it means when we choose n equals to 4. If you choose n equals to 10, then you will have a 10 points, right? And then this one becomes 10. So then this one becomes 10. So this is a pi k over 5. So you're going to have pi over 5, 2 pi over 5, 3 pi over 5 until the last one. Okay, so okay, that's n. Thus, DFT is computed this one, so that's why the DFT is computed from 0 up to 3, this one. Okay, so as below, where k equals 3 is at omega equals to 2 pi minus delta omega, which is 3 pi over 2, this one. So then this is a formula. Hk is what is the formula? So this is the general formula. Hk is a summation of that signal, and then multiply with e to the power of minus j2 pi k over n. Okay, so we will do that. So we just plug in all the values. So this is generally we have this 0 up to 3 of hn e minus j pi kn over 2, because this is 2 and then this is 4. So you slash that, you will get 2 here. So then h0 is when we replace k with 0. So replace k with 0. So this is n. This is hn. So this one, let's expand that equation. So what we have is a summation of n from 0 up to 3 hn e minus j pi kn over. So our hk is actually equals to summation of n from 0 up to 3 hn e minus j pi k n over 2. Right, so this is what we have. So if we expand this, because this is actually from n from 0 up to 3, so we should have 4 of this. So we should have 4 of this. So which is we start from h0. When n equals to 0, this is a h0. And then e minus j pi kn, n equals to 0. So this is e to the power of 0. Okay, which eventually it becomes 1. Plus h1 of e minus j pi k over 2 plus h2 e minus j 2 pi k over 2 plus h3 e minus j 3 pi k over 2. All right, expanding this equation. So you should have this from n0, n0, n1, n2, and n3. So now what we want is h0. So h0 means, so what is this is a capital H0, and this is a small h0. So small h0, this is h0. So how do we read this? So this is actually h0. This one is a H1. This is H2. And then this is H3. Okay, everything is 1. Everything is 1. So that's then this example becomes simpler. Right? So actually, you can just slash that out because everything is just 1. This is 1, this is 1, this is 1, this is 1. And e to the power of 0 is 1. Okay, so that is 1. So e to the power of minus j pi k, so now you replace k with 0. This k is 0, this k is 0, then this e will be to the power of 0, this to the power of 0, this one also to the power of 0. So this is actually those things. And we know that this is 1, 1, 1, so everything becomes 4. So that is H0. Okay. So this is what we have here, H0. So how about H1? Because we need to compute up to H3. So H1, if you expand the equation, this one, the summation of n from 0 up to 3, Hn e minus j pi n, because the k is now 1. So there's no k here because we already replaced k with 1. J pi n over 2. So expand that. So you will have 1 plus e minus j pi over 2 plus e minus j pi plus e minus j 3 pi over 2. Okay. And this thing, because you replace the n. So this n is 0. This n is 1. N is 1. This one, this n is 2. And then this one, n is 3. And actually, how to solve this? This one can be solved easily if we understand trigonometry, right? So if we understand trigonometry, because what is the exponent? Exponent is, this is just a simple cos omega minus j sine omega. Okay, cos and sine. So for pi over 2, cos omega, cos pi over 2, or cos minus cos pi over 2 is 0, because this is actually a simple example. Cos pi over 2 is 0, and then but sine pi over 2 is sorry, this is a minus. This is minus. Sine pi over 2 is 1, and then you have minus there. So that's why you get this j, minus j. E to the power of minus j pi, cos pi is minus 1. And sine pi is 0. So this is where you get minus 1. And then the last one is, this is 3 pi over 2. Cos 3 pi over 2 is 0. And then sine 3 pi over 2 is actually a negative 1. Negative, negative, then you get positive j. So this is where you have a 1 minus j plus minus 1 plus j, which equals to 0. So which equals to 0. And you can go on. This is H2. So when you plug in the value for k equals to 2, so this is what you have. 1 plus e minus j pi plus e minus j 2 pi, e minus j 3 pi. This is even simpler because everything is pi. So the sine pi part, this one, will be 0 always. Okay, so solve that, you get 0. And H3, you will also get 0. Then, so this is finally you will get this one. So what is a HK? HK is, this is a H0, which is 4. This is a H1. This one is a H2. And then this is H3. You put everything on a single vector. So this is 4000. So what is this? What is the name of this one? So this is frequency response. And it happened that our frequency response is, it doesn't have any imaginary value. So all this frequency response is just a real value. because this is a 4, 0, 0, and 0. So having our magnitude, it becomes same with HK, because everything is just real. Everything is just real. Okay. And what will be the phase? So this is, so you should have that as 0, pi, and minus pi. Right? This is for HK greater than 0. This is for HK less than 0. This is for H minus K less than 0. Because it doesn't have any imaginary value. So this is what you have. We have seen this previously. So for a zero phase system, okay, or for a linear phase system. So we have seen this. So if the imaginary is a 0, the phase is something like this. Okay, we will look on a more example after this on a phase, because a phase is not, I think previously we haven't looked, some of the sample is maybe a little bit difficult to follow. So we're going to look at more example on phase also in this week. Okay, so but for now, so that's how we do forward transform. So that's how we do forward transform. In second part later, we will look on how to do inverse, because we have two. So we have a forward transform. So we have an inverse transform. Because now forward and inverse are both using summation, so we can do all the solution. Okay, so we will start here. Any questions? Any question before we stop? So if there is no question, so we will stop. We will start again at 5 minutes, and we will look on example to do inverse transform. Okay, all right. So see you guys in 5 minutes.